Alright, so we want to talk about limits by definition, particularly of a function. So, try to get my cursor arranged here. What you've talked about is if you see this, I guess you're using C. This is not my tablet, this is a borrowed tablet, I gotta get used to it here. You've said, okay, if this is true, pretend that's a C, then as x gets close to C, f gets close to L. That's been your definition. That's sort of an emotional definition and not so much a rigorous definition. So what we want to do is make it a rigorous definition. So what does it mean to say as x gets close to, It means that the distance from x to c gets smaller. So the distance from x to c is this. The reason for the absolute values is you want this to be positive because it's distance. So you want distance to be positive no matter what. The difference between x and c is just x minus c. The distance is absolute value. And this is just because we're on the real numbers, right? So you can only have distance this way or that way because we're always traveling this horizontal line. So this is the distance from x to c, and that gets, pretend I wrote the word gets, small. Okay? There. So as this gets small, x gets close to c. And as x gets close to c, we're claiming f of x, so as this gets small, f of x gets close to L. Well, the distance from f of x to L is this. For the same reason, right? This is blah is getting close to blah, so their distance, their difference is getting small. And we just take the absolute value to name it distance instead of difference. So this gets small. I wish I had my little tablet. This is weird. Small. Well, pretend that says small. Okay, so with that in mind, I can say this means first, as this gets small, this, gets small. Right? So we want to define kind of what is small. And I'm starting out by saying, as this happens, this other thing will happen. So this being a truth, this being a fact, is what I'm claiming. So you might say to me, well, maybe it gets smaller, maybe it doesn't. What do you mean by small? And then I would ask you, no, what do you mean by small? And you say, well, I want that to be less than some number. So you define what small is. Small is just named epsilon, and you get to pick it. You get to tell me what epsilon is. And then I say, okay, well, for this to get as small as epsilon, I need to get close to x. So I get to tell you how small this has to be to make this small. So I choose how small this is. So then, given epsilon, that's given by you. You're telling me how small I have to get to prove to you that I can get that thing small. Given that, there exists delta. That's the guy I get to pick, so that when x minus c gets delta small, f of x minus L gets epsilon small, okay? So you're selecting epsilon, and I'm picking delta, and there is more than one delta I could pick. If it's true that when the distance from x to c is 0.01, then I get as close as your epsilon, then certainly if it's as close as 0.001, then it's as close as your epsilon. So there's always kind of a smaller delta. Once you have a delta that works, everything smaller will work. Also, generally speaking, we want to pick a kind of good delta as big as possible. So let me now draw this to try to show you what I'm saying. So let me just rewrite this if I can get this. This means that given, I'm going to write this. This means for all. For all epsilon, any number you pick, there exists a delta such that when that's as close as delta, f of x is as close as epsilon. Okay, so that's just rewriting what we just talked about. So if you look at that and go, oh my God, what are you saying? Rewind, watch the bit again that we just did. And this is one of those things, honestly, that you have to let settle in your brain. This isn't something that you can learn in a second. It's a little bit abstract. It's a little bit odd. It's got a lot of Greek letters running around. So you're going to feel confused, not to even introduce now things that aren't letters. I mean, they're upside down, sideways letters, but they're not letters you use at all. And such that you've never seen. So that's a upside down, sideways Greek letter, for crying out loud. So it's going to freak you out, and that's okay. But the concept itself really isn't so bad. So here's what it says. So you've got some function. So there's a function, I don't care what, and this can be open or it can be closed, it doesn't really matter, because when I'm looking at the limit, the thing that I never get to be is c itself. So what happens at c is beyond me, and I don't care and I don't know, right? So we're looking at this limit as we get there. And so what I want to do is first back this up and see what we think the limit is. L, and this is C, and then you would pick for me epsilon. So you would say, okay, here's how close I want you to be to L. How about there? And I would just come over here and see what part of this function would project into there. So I've just gone epsilon in either direction because you told me that I could be epsilon away, but not anymore. So I want to stay inside this. I want to stay inside there, okay? So I want to know for what x's does the function around here stay inside this little thing, and it's these, right? So then I'm going to choose a different color. So then, graphically speaking, so I come over here and I say, okay, well, I'm going to go straight down from there and straight down from there. And I want to know how far can I go from C. I'm trying to figure out how close do I have to get to this guy so that all those function values live in there. So if I go, say, right there, let's say I pick this little bitty tiny delta, then everywhere up there is contained in this strip, which is what I want. So whatever this distance is an option for delta. This one might be an option for delta. But the thing is that I need the entire thing to be contained up there. So this delta, this looks bigger to me. So if I go this far in both directions, I get outside that strip. See right there, I'm outside the strip. So I need to choose the smaller one. So if for example, C was 4, and you chose your epsilon, and when I brought these down, I ended up with, say, 3 and 4.5. Well then, on the one hand, I have a distance of 1, and over here I have a distance of 0.5, and I have to choose the smaller. So that would take 3.5 to 4.5. All of that would map inside, but 3 to 5 wouldn't. Okay, so you have to pick the smaller one so that the whole thing gets in to there. Always go smaller with delta if you have to. If you have to kind of throw stuff away to find the answer, that's fine, but you can't add stuff. So don't round, throw away. Okay, so let's look at this then by definition, and let's look first, say, at a line. So I'm going to say the limit as x approaches 4 of 1/2 x plus 3. This is continuous. I'm just going to plug this in so that I get 5. Okay, so that should be the limit. I'm doing one where you know the limit. Normally it'll be given to you if you couldn't figure it out. So what we want to do then is we're going to be given an epsilon, and let's say it's 0.01. Then we want to find delta, so that when x minus 4 is less than delta, f of x minus 5 is less than 0.01. So all I have filled in so far is C and L. So now I'm going to say, okay, here's what I want. What I want is for 1/2 x plus 3 minus 5 to be less than 0.01. And my end goal over here is x minus 4 in absolute values, less than delta. So I'm trying to find delta. Everything else is an x or a number, so I'm in good shape. So 1/2 x minus 2 . Now you could pull this out and put less than 0.01 greater than negative 0.01 if you remember that from absolute value. What I'm going to do is just multiply through by 2. If I multiply through by a positive 2, nothing happens anywhere. The absolute value stays the same. So if I multiply through by 2, I already get delta. So this case, you have a delta because this is a line. So if I have a line and I go the same amount in either direction there, then it goes the same amount in either direction there, because that's what slope does, right? So with a line, you're going to have the same delta in both sides, okay? Okay, so what about something that isn't like that, where the difference, the deltas will be the same on both sides, kind of? So let's look at okay, so I'm going to look at the cube root of x. If I plug in 1, I get 1. So hopefully this will be equal to the limit, but cube root x looks like this, so I think that my delta should be different, right? Because we have this kind of curvature going on. So remember that I want delta so that when x is less than delta away from 1, cube root x is less than, oh sorry, let's say epsilon. is less than 0.01. Okay? So here's the thing now. I don't have any way to kind of get that x by itself. I need to make it look like this. I need to manipulate it until I have x minus 1. But with this one, there's no way to kind of factor it or anything. So what I need to do is separate this. So I am going to put in the step where I put the definition of absolute value. The definition of absolute value means this. Okay, so if the absolute value is less than 0.01, then the whole thing is trapped between negative 0.01 and 0.01. And then I'm going to move the 1. So I'm going to add 1. Now I can cube it. So because it's cubic, it's just increasing. So if this is less than those two, then this cubed is less than either of those cubed. So 0.99 cubed so I'm going to go find out what these are. So I've got 0.97 and 1.03. And then back over here, because I don't want x, I want x in absolute value, but I want x minus 1. So x minus 1, this minus 1, and this minus 1. So the 0.99 cubed minus 1 is negative 0.0297. Okay, sorry, Miss Edie brought me a charger for my phone, so I had to stop a second. So I have negative 0.0297. .0303. Now, here's the thing, when I turn this to absolute value, I need to have the same number on either side because x minus 1 and absolute value less than delta means it's between delta and negative delta. So I need these to match. But this is the only fact I've got right here, okay? We want it trapped so that we don't have any extra to map on the outside. So generally speaking, so our options for delta, let's say, are 0.0297 or 0.0303. And we need to pick the smallest delta. And furthermore, like what I was saying about the rounding, so we have this 0.029701. You can keep the 0.1, maybe, depending on if it was rounded. But the safest thing to do is to kind of drop it. But if it said 0.029699, you would not round that to 7. You would still truncate because you've got to stay as smaller. So 0.0297 is the delta that we would choose for this. So hopefully this is somewhat clear. I actually really love this topic, but you do need adjustment time for it. It's really pretty fun. It's kind of like a puzzle, and just remember that when in doubt, you should throw away the extra, get a little smaller. You could theoretically almost always in problems you're given in calculus say, I choose delta equal to 1 billionth, and then set forward to prove it works, but that's not really great. So we want you to do the kind of understand what's happening and do the algebra. And then the way that you would check it is you would just claim now that x minus 1 was between negative 0.0297 and positive 0.0297. And then add the 1. Well, here. I'm just going to do this quickly. Remember that our goal is to have, by the end, cube root x minus 1 less than 0.01. Okay, so I've chosen so I have that delta, so then I still have this problem of I can't randomly take the cube root of this, right? Because then I'd have the cube root of all of x minus 1, so I still need to separate this out. Oops. That was an accident. Okay, so I'm going to add 1. And now I've got 0.9703, and I need to take the cube root everywhere. So I forgot 0.9703. Cube root. So that's 0.99. And 1.0297. $1.0098. And then I would subtract 1. And I'm going to just state real quick that that's less than 0.01 right there. So, oops, minus 1. So because I have negative 0.01 and 0.01 over there, then I get that the absolute value is less than 0.01.